This is the recording for the pendulum lab. So this is the lab manual, and we're going to go past the motivation and objectives, and then the theory. In the theory, there will be a few that are called a rectangular cuboid, so you need this equation here, volume equals length times width times height. One of them will be a sphere, so you need this equation here for the lead sphere that you will see. And I don't think there is a cylinder or an ellipsoid, so you have to go back to these two equations at some point. Alright, I'm going to go past this one here. On this page here you will find two different methods to determine the immersed or effective mass, and therefore the specific gravity of an irregular shaped specimen. And this is one method here where you hang it on a spring scale, and here is another method where you put the beaker on the scale first, and this is the one we're going to use. So keep in mind that when it comes to that, we're using what is called the immersed mass. So the one on the left here, you will see that in the video. And then when you scroll down, you find this equation here, which is the specific gravity is the typical mass, the actual mass of the specimen divided by its immersed mass. That's all it is. And then you attach units to it, grams per cubic centimeter, in order to get density. The number between density and specific gravity is the same, just one has units and the other one doesn't. Alright, and here's the equipment that I'm using. Yeah, pretty much. I'm not using the tape here, I'm just using the caliper. Alright. So here's an example. It's an old example for brass. I made another example for copper, and I will do that a little bit later. I will go through all these numbers here. This is the first one that I measured for you, iron or steel, and I pretty much already put the data that I measured in here and also the absolute errors, and I will explain them in a little while. And then you have to do the remainder of the calculations, and I will take that copper example and will tutor you through it. So here's aluminum. I know I called it aluminium, but either way. And again, I put the data in here and the absolute errors, and again I will explain that later. Here's the lead sphere. You would have to compute the radius. Well, that simply comes out to 1.78 centimeters. And then here's the water. Notice here mass of empty can is 0 grams. You will see that how I tiered the balance in the video. And then here's the pirate, which is fool's gold. And here are the measurements for the mass. And remember, this is the immersed mass here. The last one here, you don't need this one because you didn't do the effective method mass, or I didn't do it. And then here are the lead also as an immersed mass. And again, I don't need this one here, but this one is the immersed mass. And that's actually it then. Notice that I said skip the conclusion. And then in the addendum, I know this is about the error calculation, but you will see that instead of using this complicated square root, I will just have you add the errors when it comes to that. All right, here are the videos that I taped earlier. So in the next few minutes, you will see the videos. And then I get back to actually doing the example calculation for the copper specimen. This is my second take for determining the density of these objects, and I'm going to do the copper cube, and then the steel cuboid, and then the aluminum cuboid. And I know that this one is steel because it's much heavier with its larger density, which we're supposed to determine. And then of course this is aluminum. And over here I have the lead ball, and I'm not going to do the brass cube here. It is in the lab manual, but I'm going to use a new example, which is the copper cube here. Alright, I'm going to measure this one here, and this caliper here measures in millimeters, but density is given in grams per cubic centimeters, so I would have to convert that. So for example, right now it says almost 32 millimeters, which means it's almost 3.2 centimeters. I just have to keep that in mind to always divide my numbers here by 10. And that, of course, is the beauty of the metric system. It's so easy to convert between things, which in science and anywhere we have to do a lot. All right, so this one here says 31 point something millimeters, and I'm going to see which one lines up here, and the one that lines up the best is the 8. So it's 31.8 millimeters, which is 3.18 centimeters. Then that was the length. It's a cube, right? So length, width, height. Oh well. That one also is 3.1 over here, and then this one here that lines up the best is the 7. So 3.17 centimeters. And then the height. And I'm going to come up again 3.1 something, and the one that lines up the best is the 6, so 3.16 centimeters. And I just want to make sure that I'm still taping actually, so it doesn't surprise me that I do the second take, and again I just have 3 seconds. Alright, so these are the dimensions which I jotted down over here and put on the lab sheet. Then I'm going to determine the mass of the copper cube. And this one comes out to 294 grams, which, by the way, is the exact same number that I measured yesterday when I had my first take. Notice that it has a hook, and I cannot remove that hook, so I will have a systematic error here. By the way, as far as the scale is concerned, the absolute error that I get, maybe this can be shown on the camera. I know it says 0.4 here, but it could go 0.1 higher, 0.1 low, and the absolute error is half of that, and that's why you will see in the lab manual 0.05 grams is the absolute error. Alright, let's go to the steel cube. I might as well, since I have the scale already on, I'm going to determine its mass, and it measures 171.1 grams. Absolute error, of course, being the same. I can turn this off here for a little while. Alright, so here I'm going to have the length, and so here it is just beyond the 3.4 centimeters, and the one that lines up the best is the 3 over here, so it's 3.43 centimeters, and that is a little bit over, how much is that, like an inch and a quarter? No, it's a little bit more than that. It's like 1 inch and 3/8 maybe. So that's how that must be cut. Anyway, 3.43 centimeters. This one here actually does look like an inch. By the way, the copper cube earlier was actually an inch and a quarter. That was 3.18 centimeters and so on. In any case, for the steel here, it is just beyond the 2.5, and I'm reading 2.52. So this one lines up the best, 2.52 centimeters. And then the height, so to say, length, width, height. So height here is just beyond the 2.5, and then 2.54 lines up the best. So apparently this is really cut exactly to 1 inch, which is 2.54 centimeters. All right, I already got the mass earlier. I'm going to do the aluminum. This one here, by the way, looks like 2 inches, right? So the caliper I'm measuring almost 5.1 centimeters, so 5.0 something, but the next digit is going to be rather large, and the 9 lines up the best. And I actually am going to see if this is actually in the photo. I think it has been in the photo all this time, and I'm going to move a little closer anyway. So I'm filming sideways here, not over my shoulders, so I actually have to look. I have to look for it from the side, while you look at it from a front view here. But I don't know if you actually can see these numbers here. And anyway, I have 5.0 here, and the one that lines up the best is the 9. So I have 5.09 as the length. By the way, the error on this one also goes that I can go like this last digit here, I can go 1 lower and 1 higher, so it's plus minus 0.01 centimeters, but we're taking half of that as the absolute error, and that's why you will see on the in the lab manual 0.005 centimeters is the error overall. Okay, let's do the other 2 dimensions. Again, this looks like an inch on each side here, which means relatively close to 2.54. This one is 2.5, and then in the middle here, so, and the 4 lines up the best, so 2.54 centimeters. And then this one here, also 2.5 something. And then 4 again lines up the best, so 2.54 centimeters. All right, let's determine the mass. This one says 89.2 grams. Yesterday I had measured 89.3 grams, but I'm going to use today's result. So did it lose 1 gram overnight? Probably not. It's probably what the scale does behind the scenes, that it needs to round as it measures, and then it's either a little bit up or a little bit low, and that's where you get that 0.05 gram error in there. Okay, so 89.2 grams. Might as well measure the lead ball. This comes from a fishing store. 277.3 grams. Alright, I don't need this one anymore. Determine the diameters. Again, I have to check if it's actually still recording, and it is. And boy, I only have 50 seconds left. I think I start a second recording here. Alright, so I'm going to determine the diameter of this lead sphere here, and I have it 3.5, and then the one that lines up the best seems to be the 6 actually, so I have 3.56 here, but of course it's pretty, you know, there's dents in it, so I'm going to measure another diameter here, and this one here is going to give me 3.5, this is really tough to do, 3.57, and then over here I'm going to have 3.56 again, and then over here 3.5, and 5 lines up the best, so 3.55, and then I take an average of those. Well, that's easy to do. That's going to come out to 3.56 centimeters, and I have to determine the radius from that, which of course is going to be 1.78. Notice again it also has a hook, which means it does introduce a little systematic error to the mass. Alright, and those were the 4 objects that I want to measure, and then I'm going to do the example calculation for the copper cube next, and then after that I'm going to determine the water and then the irregular shaped specimens.
So here's the example calculation for the copper cube, and then use that example calculation to figure out the others. I'm going to do the density and the volume first, so I'm going to just look at these numbers and come up with the volume over here, compute the density from it, round the density. After that I'm going to look at the errors. So here we go. Figure out the volume first, multiply these 3 numbers here. So here we go. I think I'm typing off screen because not my entire calculator fits on the screen. So there we go, 31.854696, there it is. At this point I'm going to take them all along because this is an intermediate result, so I will actually use them to compute the density. So I'm going to divide 290.4 by this number here. I don't have to actually retype it because the TI-84 allows me to divide by the previous answer, hit enter, and I'm going to come up with this one here, and I wrote it all down. Okay, now the thing is I need to round it. And let's see, there it is. That was actually a little bit off screen here. So I need to round it here. So I have to make a decision, where do I round it? Well, with the significant figures, it gives us a clear understanding of saying, okay, I got 3 sig fig here, not decimals. Significant figures is not the same as decimals, okay? So I have 3 significant figures here, 3, 3, 3. Here I actually have 4. I have to go with the least amount, so 3 significant figures. So this number here rounds to 9.12, 3 significant figures. Okay, on this particular one here, all the rest here this is irrelevant, except for the 6 here perhaps, because it rounds it down up to 9.12. But the thing is that if you have already an error in one of the first 3 digits, significant figures, then you have completely different numbers way back here. So these are irrelevant and could be considered garbage. Throw them away. You don't need them. You cannot pretend that the result is going to be more accurate than the measurements. If you measure to 3 significant figures, the result can only be 3 significant figures. If you measure 1 significant figure, which by the way is kind of like an estimate, then your result cannot be 5 sig fig. It has to be just 1. So in this case, 3 significant figures, or 4 for the mass. Use the smallest one, so it rounds to 9.12. But I want people to write down this ridiculous result from the calculator to point out there is no point of the stuff here in the back. This is micrograms per cubic centimeter or something. It has no meaning whatsoever. All right, so that's the calculation for the density and a long discussion on significant figures. Okay, let's look at the absolute error here. So I found this applet here, and this one here, I prepped this length for this little cylinder here. I'm going to push the caliper on here. Notice that the numbers are always changing, and as I said, I try to prep it as close as I can. There we go. All right, so this one is squeezed in here. Notice that I'm going to look for where the 0 is actually right here. It's just short of the 3.2. I know it says 3.1 here. What that means is, since the 0 is short of 3.2, I'm measuring actually 3.1 something. And now I'm going to look at which of these little lines, these are fine detailed lines, are lined up the best, and it already tells me that the 8 is lined up. And that gives me the last digit here, so the 3.18. And as I said, that's kind of like the copper cuboid that I measured the length for. So 3.18. Okay, the error of that is half of each of these little marks. Well, half of each one of these is half of 0.01, so 0.005 centimeters, and that's what you will see as the absolute error in the tables. And, whoa, oh, I pushed the wrong thing off. All right. So here, that's where you see that 0.005. All right. Then I'm going to determine what the percentage error is. So I'm going to pull up my calculator again. So the percentage error is being determined as the absolute error, 0.005, divided by the actual measurement, 3.18, and then multiply by 100. Okay. The percentage error should only have 1 significant figure because the absolute error does as well. So I'm going to round this one here to 0.2%, and then you can see if I divide by the width and the height, which are virtually the same, I'm also going to come up with 0.2. For the mass, I'm going to divide 0.05 grams by the actual measurement of 290.4, and I come up with that, again multiply by 100 to get it into percentage. And again, just 1 sig fig is needed because the error itself is only 1 sig fig, so 0.02%. Then in the addendum you find a calculation on how to do the errors properly, but here I'm actually telling you just simply add them. So 0.2 plus 0.2 plus 0.2 plus 0.02 is 0.62, but again the error only takes 1 significant figure, so 0.6%. Okay, what's the absolute error on the density? Well, here I kind of have to go backwards. So, whoops, okay, I didn't mean to pull that one up. Where's my calculator? There we go. All right, so here I'm gonna, instead of dividing as you saw earlier, I'm gonna multiply the percentage error times the computed result for the density. So I'm gonna do 0.6. Okay, I know that's a little bit off the screen. 0.6 times 9.12, I come up with this number, but oh, it wasn't 0.06, it was 0.6. I'm sorry. It's Wondering why did I come up with the same thing, with the wrong thing here. So I'm going to do that. Oh, come on. Can't be this hard. There we go, 0.6. Come up with this one here, but since I was in percentage, I have to divide by 100. So there we go. So I come up with a rounded 0.05 grams per cubic centimeter, and that's the error that you see here. So it is 9.12 plus minus 0.05. That still doesn't quite fit the published density for copper, which is 8.96. But remember, there was this hook attached to it on the top. And it just so turns out if I was to subtract exactly 5 grams from the mass here, I don't know the mass of the hook, I'm just guessing 5 grams. If I actually do that, I come out actually with exactly that published density for the specimen. So expect really good results for the others as well. And that's the example calculation.
All right, so this is for the water. I figure I'm going to use a graduated cylinder here, so instead of an empty can. So I'm going to put that on a scale, and I know it gives a reading, but it's really nice that the scale has a tare button, so I'm just going to tare it to 0 as if this is 0. Okay, I'm going to pour this one in, and let's see what we get. Oh cool, we can hear that the pitch is getting higher and higher, right, as I pour this one in. So I'm reading 23.6 grams for mass of the full can. And remember that my empty can, so to say, or gray cylinder, actually has 0 because I was able to tare it, so 0.0. Okay, and then I'm going to read off how much I actually have in here. I'm going to look at the meniscus, and this is really strange trying to film this and at the same time get a good measurement. So I'm reading off 23.2 milliliters, which is also 23.2 cubic centimeters. That's what I meant to say. All right, that's actually it for the water. All right, and that's to determine the specific gravity of an irregular shaped specimen. So specific gravity is the same thing actually as density, except it doesn't have any units, but as it compares itself to the density of water, which by definition is 1.000 grams per cubic centimeter, that means that the specific gravity actually comes out to the same number as density, and then we just have to attach a unit to it. Anyway, so I got this pyrite, so to say, the fool's gold here, but you can see that it sparkles. However, there's lots of other minerals in here, and I'm going to turn on the scale, I guess. And this one measures 32.4 grams. And then I'm going to do the lead ball. I know it's not quite a irregular shaped specimen, but I'm just going to measure it twice. I could use the 277.4 grams from earlier, which is actually what it says, what it shows again. All right, then I'm going to put this beaker of water on here. And it measures this much, but again, I'm going to tare it. Okay, and now comes the trick. Usually this is done with an overflow cylinder, but I believe the method of using the immersed mass is actually better. So I'm going to immerse the lead in here. That means that the scale is going to measure the mass of the lead ball minus the buoyant force that is acting on it. And that is what's called the immersed mass. I have to hold this pretty still, and the scale goes a little bit up and down. I guess it is 24.9 grams for the lead. 24.9. That is the immersed mass for the lead. All right, then I'm going to do the pyrite. I have to see if this is still tared. Apparently the lead didn't take any water with it. Interesting. It's still at 0.0, so here comes the pyrite, fool's gold. 9.0 grams is what it says. And when you determine the specific gravity of that, I can already see that it's going to be off because this is not a pure pyrite. All right, and that actually was it for the entire experiment on density.